Friends, in this video, let us discuss the biasing circuit with biasing done to BJT circuit, which is collector to base feedback resistor biasing. Okay, so now why this particular circuit is considered to be collector to base feedback? If you see the circuit, you have a resistor RB which is connected as a feedback from base to the collector. So that is the reason it is called as collector to base feedback resistor. Now let us write a diagram, or else I will try to mark the current directions and also the current terms in this particular collector to base feedback resistor diagram. If you see here, I do have a VC at this point. So we have a voltage measured at the collector terminal, which we know that it is VC, and we have a voltage measured at the emitter terminal, which we call it as VE, and we have a voltage which is measured at base, which we normally call it as VB. Now we do have currents passing through collector is IC, passing through base is IB, and we have a current through emitter which is IE. Okay. Now as we see here, IC and IB, the current directions which are written towards collector and base, the current flowing through RC will not be IC now. This will be the current entering the node, which is equal to the summation of current leaving the node. So if you see from at this node, the current leaving this node is one direction is IC, and in this direction it is IB. So therefore, the summation of IB and IC is the current which is flowing through this particular branch. Okay, so it is the current which is flowing through the resistor RC. Okay, now coming to the equations that we write. So as we all know that for DC point, the DC load line Q point, locating of Q point in DC load line, we need to know what is the equation for your collector current IC, and what is the equation for the collector emitter voltage VCE. Okay, so this is what we need to know now. Fine. So to do that, we need to analyze this circuit now. Okay, so let me go with that. Now to find out what is IC, to find out what is IC, we need to write the equation for IE. Okay, we need to write the equation for IE. Okay, fine. Before that, let me try to tell what is VC. Now we know that in the previous video I already told you that VC and V, whatever we measure, so your VCE is between collector and emitter, which is VCE, right? So this was been told in the previous video. So therefore I can say VCE equals VC minus V, VC minus V. Now if you carefully observe, if you see the circuit properly, your VE is what? See, emitter is directly connected to ground. Therefore, I can easily say that VE equals 0. Due to which, I can say my VCE is equal to VC only. So, whatever the voltage I measure from this node is what VC. And you see that as V is 0, you will be able to see that VC is nothing but the collector emitter voltage only. Okay, fine. Now let me take go with the equation for VC now. Now to find out the equation for VC, let us go back to the circuit now. We know that this is VC. We know that the voltage at this point is VB. And we also, okay, to write the equation for, VCE, what I'll go do is, I'll go with the loop to write the equation. I'll go with the loop from VCC. Now I'll go like this, and then go like this, then go like this, and in this way. Okay, so this is the loop which I'm going to consider to write the equation for for this particular loop. So that let me see whether I will get VCE, which is nothing but VC. Okay, so if I write the equation for that loop, what will I get is, I see that the current through the RC circuit, right? The current through RC circuit is, your RC circuit is IC plus IB, and the current through this is IC, whereas the current through RB is IB, and we also know the voltage between base and emitter is considered to be VBE, which is zero point 0.7 volts, right? So if I write the equation in for this particular loop, I can say that VCC minus IC plus IB into RC minus IBRB minus VBE equals 0. So this is the KVL equation which I wrote through the loop which I have taken in this green color. Okay, so we know that now what I need to do is I need to write the equation. I see. So I need to get IC. So now what I need to do is I need to transmit, convert this IB in terms of IC. We know that IC equals beta times IB. So therefore, I can easily say that IB is equal to IC by beta. Okay, so you substitute IB in terms of IC by beta. So for that, what I'll get is VCC minus IC plus IC plus IC plus IC by beta into RC minus IC by beta into RB minus VB equals 0. Now if I take VCC minus VB towards left hand side, and I will take this IC by beta into RB and RC into IC plus IC by beta, I'll take to the right hand side, and if I take IC common in these two equations, I'll be getting 1 plus 1 by beta into RC plus RB by beta. So therefore, what I'll do is, if I take the LCM, finally what I'll get is, in this right hand side, I can say IC into beta plus 1 into RC divided by beta plus RB by beta, and you will be able to get VCC minus VBE towards left hand side. Now in this case, if I say beta is very high compared to 1, so definitely beta is very high compared to 1. A normal transistor, for example, we have a transistor which is named as SL100 and all, where beta will be almost equal to 100. So beta is very high, therefore I can say beta plus 1 is approximately equal to beta, and I can easily say that this particular term, if beta plus 1 equals beta, this beta plus 1 gets cancelled with beta. So finally, I will be left out with VCC minus VBE equals IC into RC plus RB by beta. Okay, IC into RC plus RB by beta. Therefore, finally, you see that IC is equal to VCC minus VB divided by RC plus RB by beta. If I do certain considerations here, saying you know that my VCC is very high compared to VB, because VB is 0.7 and normally VCC what we apply will be 10, 12, 15, 30 volts like that. So therefore VCC will definitely be greater than VB, and if I choose RC such that it is very high compared to RB by beta, then I can easily say that this numerator will become VCC, and if RC is very high compared to RB by beta, this will be just RC. So finally I can say that the value IC will be equal to approximately equal to VCC by RC. So this is what the value for IC that we got for collector to base feedback connection. Collector to base feedback connection. Now coming to VC, which we already told VC is nothing but VCE. Now if you take the loop, now if you go back and look into the circuit for VCC, for VCE, let me erase this. Now for VCE, you see VC. So what I can write here is the voltage from here to ground is actually, your VCC, and the voltage from here to ground is actually your VC. So I can say that, the VC, now this remaining voltage would be equal to, we know the current is IC plus IB, and that multiplied by RC will be your, voltage equation across this. Therefore, I can easily say that my VC equals VCC minus IC plus VCC minus IC plus VC equals VCC minus IC plus IB into RC. IC plus IB into RC. We can also write this as VCC minus IC into, if I say IB is, we know that IC equals beta times IB. We know that IC equals beta times IB. If I substitute that here, I can say if IC is taken common, I can easily say it is 1 plus 1 over beta into RC. Okay. Now, if I take 1 by beta, definitely it will be less than 1. Earlier we said beta is greater than 1, right? So if beta is very high than 1, then 1 by beta will be less than 1. So finally I can easily say that my VC is equal to VCC minus. Now if 1 by beta is very less than 1, this will become 1. So therefore my VC will be equal to VCC minus IC RC only. So therefore this is the equation for VCE, and this is the equation for IC. Now these are the 2 points which we normally, these are the 2 values which we consider for locating the Q point in a DC load line. I hope you got the derivations what I did in this video, and this is the biasing circuit which is called as collector to base feedback resistor biasing circuit. Okay, or if they say feedback biasing circuit, then it is considered to be collector to base feedback resistor bias circuit. Thank you.